Good afternoon, class. So there's this thing in our universe that we've been talking about called electric charge. It's a fundamental property in our universe. There's lots of properties that you might be able to use to describe something. So when I want to describe something, I might describe its size or location or color or smell or things like that. Those are not fundamental properties. Size comes from the fact you have a right and a left. That's not fundamental. Smell is manifested by lots of physical and chemical things happening. But there are a couple things that we can describe as fundamental. Electric charge is one of those things. That it's just a property of our universe. Some things have it, some things don't. And so what we've been talking about the last few classes is that charge, there's a charge up there, my plus Q right there. Charge creates something called electric field. Electric charge creates electric field. That's an area of influence around that charge. And already we're getting into some cool magical stuff because it goes out to infinity, it goes through all space. And so I can actually push and pull on other charged objects if I'm creating a charge. So charge creates field, field pushes and pulls on other charges. So we've already seen that when we use the microwave to create electric fields. Those electric fields pushed and pulled on other charged particles like the electrons in my Hot Pocket or whatever. Or at least the polar molecules in my Hot Pocket. Okay. So there's this fundamental property called charge. Charge creates field. Field pushes and pulls on other charges. You and I are made up of charged particles. Every atom in our body is made of charged particles. Our protons, which hang out in the center of our nuclei, those are positively charged. The electrons that fly around the outside, those are negatively charged. So that means everything you are familiar with is made up of charged particles. I'm made up of about 7 billion charged particles. That's a 7 with 27 zeros after it. And that's all of my atoms. Each one of those atoms has positively charged protons in the middle and negative electrons on the outside. That's all of them. So when I talk about hydrogen, when I talk about carbon, oxygen, all of them look like that. So there's a picture of who knows what atom that is. But that's all matter. So the chair you're in, the pencil you're holding, the table you are writing on, all of that is made of these charged particles, which makes it fun because I can mess with those charged particles. As you can see from that picture, I've got all these electrons on the outside. Those electrons don't have a terrible affinity to their parent atoms. And so what we've been doing in the last couple classes, we'll continue to do today, is you can mess with those electrons on the outside. And so a slightly better picture, so that's one atom, a slightly better picture of matter is a whole big collection of those. And so you can think of anything, whether it's me, you, or a piece of rubber, or fur, or balloon, or whatever. You can think of that as a kind of, the word I've used a bunch of times is like a lattice, just a collection of positive nuclei with electrons swimming all around it. Now, different materials conduct those electrons better than others, but we're actually not even that worried yet about conduction, about moving electrons. We like to just be able to kind of squeeze those electrons. And so, hey, glad you made it. So we like to be able to just maybe push those electrons around or just grab them or mess with them. And so I don't have to be a conductor to be able to do that. And so my hair or rabbit fur or that pesky balloon, that is made of atoms, that's got electrons on the outside, and I can mess with it. So we've talked about this triboelectric series, and again, my picture of amber is just a reminder, the word electron means amber in Greek. Amber was one of the first materials that apparently, I guess, at least the Greeks realized, wow, if you rub that against wool or something, it becomes charred. It's got this thing called charge, which they had no idea what that meant, but it exhibited these properties where it would, like, stick to things, or you'd end up with dust collecting on it because it was staticky. So I think a lot of Greeks discovered staticky stuff, and then hence we now use the term electron for a charged particle. Okay, so we've talked about our triboelectric series, and that's just who usually wins the battle when I rub two things together. And so, like I said, you don't even have to do any rubbing. You can just, what would I like to charge? I'm going to charge this piece of Teflon with this silk. I literally just do this. Just by doing that, I'm actually stealing electrons, and I'm charging this thing up. And that has a lot of cool properties, a lot of cool effects. That today we're going to look at several effects of that. The most fun one is our Van de Graaff machine. So we'll play with our Van de Graaff machine again. So if you have nicely clean and conditioned hair, you might want to prepare yourself for a trip up to the Van de Graaff machine, which we'll play with that later. Before we do that, I would like to look at just a couple other examples. First, we did this the other day. I'm always in a rush to get through. Stuff, and I run out of time. So I want to revisit my two electroscopes up here. An electroscope is just a tool to demonstrate or show electric charge. And so I've got two electroscopes up here. Here's my old-timey picture of what an electroscope is. It's a bunch of conducting stuff, first of all. And so I've got a conducting disc, or in my case, a ball at the top. That's metal. And so I'm sure we've said this by now in this class a couple times, but now for sure we need to know what a conductor is. A conductor is something that the electrons are very mobile. Given a little push, they'll get going. And so we'll talk later how you give electrons a push, but you stick them in an electric field for one. And so if I have a conductor and I put them in an electric field or just get them going or give them a push, they'll flow, they'll get going, they'll create current. And so that's a conductor. So some examples of a conductor: the metal ball on the top of my electroscope, the metal shaft going down from that ball or disc in this picture, and the little leaves at the bottom all are metal and they're all touching. They're all metal and they're all touching. They're insulated from, in this case up there, it's a jar, and here I've got a metal, a little metal case, but they're insulated from that. But I can demonstrate electric charge pretty well, and what I'd like to do is demonstrate induction. I'm inducing charge or a charge separation when I do as they're doing in that picture. So hopefully we'll be able to see it here. So I'm going to charge up my rod. It's going to be negative because it's Teflon and silk. I think that if I remember my triboelectric series right. Now what's going to happen is I should be able to induce charge. So what's happening in this picture, I think I'll be doing the opposite in that picture. Either works. So I think I'm going to negatively charge this because I've got Teflon and silk. I'm going to negatively charge this. So I've got a bunch of negative charges. This is an insulator. This is an insulator. And an insulator, the electrons they're still protons and electrons. They're just not very mobile. And so when I put a bunch of electrons right there, they're going to stay there. I don't have to worry about them running down to my hand or anything. They're pretty much fixed. So I've got a bunch of electrons on there. And as you probably know, like charges repel. If we didn't learn that in high school or something, there's your big lesson of the day. Like charges repel, opposites attract. We definitely need to know that. So all the electrons in that metal are going to run away. They're mobile because it's metal, and they're going to see this coming in, and they're going to run away from it. And you should be able to see the leaves run away from each other or repel from one another. So what I'm doing is I'm taking electrons here, bringing them close to this metal ball. The electrons in that metal ball get as far away as they can, and how they get as far away as they can is by running down into those leaves. So I'm doing the opposite of what's in that picture. In that picture, those are positive. I'm pushing negative electrons. They're going to get as far away as they can, and they're going to collect down on those leaves. And you can see when I bring the stick close, they separate, and when I bring it away, they go back because my negatively charged rod is gone. Now that's induction. Now I should be able to get some to conduct if I touch it. And here's why. When I bring this negatively charged object up here, the electrons are going to run away, leaving a net positive charge on that ball. I'm going to leave a net positive charge on that ball, negative charge down below. And by the way, this is going to come up several times today, so I want to make sure we're clear on this. Just about everything up here right now, at least right now, is neutrally charged. I'm neutrally charged. The Earth is neutrally charged. I'm going to wave my hands in this picture, I guess, to, I don't know, that helps. But I'm neutrally charged. By neutrally charged, it means I have, like I said, I have 7 billion protons and electrons, but they're about cancel out. So they're about even. So I've got a ton of positive charge, but I also have almost the exact ton of negative charge, so I have no net charge. I'm neutrally charged. This electroscope is neutrally charged, but I can induce a charge separation when I chase the electrons down onto those leaves. So I'm going to induce a charge separation. Now then, if I actually touch it, the leaves should stay apart to some extent. So I should be able to charge up this rod, because right now I'm touching it. And so you can see that the leaves are kind of stuck. Hopefully it's on that. Is that even visible? Hopefully you can see that on the camera. That's good enough. Okay, so right now I have actually charged up that thing. It is no longer neutrally charged. I've charged it up by conduction. So what I did is I chased the electrons away, leaving the top with a net positive charge. And so then when these negative charges, which would like to get away from each other actually, because they're all negative, they repel, given the opportunity, by touching them to the positive ball there, the electrons jumped across. This now has a net, yeah, you can see that pretty well. This now has a net negative charge. I am conducting, I am pretty neutrally charged, I'm touching the ground. So when I do this, do we see the leaves fall back together? I just grounded that thing. That's the term for that. And it's a pretty good term. The word we use in electricity, and we're going to use it a lot for the next couple weeks, the word we use is grounding. And it's a good term because the earth, the ground, is our biggest and best place to just dump electric charge. So our earth, which is very, very large, we can just dump electric charge all day long. So if you ever wonder what the third prong and the plug is for, it's a ground. It's a route to ground. And so electrons would like to, if any electric charge wants to get away from itself, a good place to go is ground. So right now I'm grounded, and so you can see I can charge this guy up by conduction. Let's get some charge on there. You can see those leaves start to get separated. Okay, those leaves are pretty well separated. Now I'm pretty neutrally charged. I'm grounded, and I can ground those guys. Okay. That's an electroscope, just a simple device to demonstrate induced charge separation, conduction, and then grounding. Okay. My other electroscope operates pretty much exactly the same way. I'll do that real quick. Hopefully that one will also work. This guy sometimes doesn't want to move. There we go. So I'm going to continue to charge. That guy's now supercharged. There he is. So pretty not visible in that shot. There he is. Oh, and then when I actually go up, touch it, I can ground it. Okay, now it's grounded. So that's just another version of electroscope, pretty much the same idea. Any questions? Cool. Okay. So last class, I think someone gave me a joke balloon or something. I just refused to get charged. Just to not make the same mistake again today, I tested my balloon. It works really well. So I've got another balloon, and I've charged it up pretty well. I should probably recharge. Or maybe my shirt wasn't made of cotton. I don't know. I had some problems last class. So I've got another balloon that I can... Dang it! That balloon that might not be my only good balloon. I wonder... I wrote on that balloon with Sharpie. I wonder if the Sharpie ate the balloon. So here's what we're doing. I'm going to try again, hopefully. So there was no glue on that balloon. Okay, we'll see if this one works. So here's what we're doing. I'm hoping I can get this balloon to stick to the block. Yay, okay. Hey, thank you. That is the best thing right there. That's the highlight of my year. So here's what I want to show. First of all, what we're seeing in that picture right there is what's going on the board over there. I have, using tribal electrification, cotton rubber, I've electrified the balloon. The balloon is an insulator, so where I put the charges, they're pretty stationary. And so I put the charges on one spot on that balloon, and they're going to stay there because it's an insulator. Then I took that balloon, which now has a collection of negative charges in one spot, and I brought it up to the wall. But as I brought the electrons up to the wall, that extra electrons, those electrons chased the electrons on the wall away a little bit. Now the wall is an insulator, so those electrons are not mobile. They didn't just flee away to the ground. But as I try to indicate in my slide there, they're just hanging out slightly to the right of on their parent atoms. So the electrons are just kind of, the electron cloud, if you remember chemistry class, is just kind of squeezed over a little bit, leaving a slight polarization or an induced charge. And just to show that, and this, who knows, maybe the Sharpie eats balloons, but I wanted to show that, so right there is the opposite. Hopefully you can, definitely not, can't see that on the camera, but hopefully you can see my little plus sign up here. And so if I were to displace this balloon, you see it goes back to that spot. And if I kind of displace it this way, it goes back to that spot because there's one spot on that balloon where I've got charges accumulated. And so if I tried to put this balloon this way, it's probably gonna, well, it's now sticking in me. Okay. But if I tried to stick it to the wall somewhere else, it's going to try to rearrange so that the electron where the extra electrons are is in one particular spot. Okay, that's going to wobble its way down. Okay, any questions about that? Okay, so that was just rubber and cotton that we were using right there. Rubber's kind of in the middle-ish. Cotton slightly above it. So the rubber was, yeah, definitely collecting some negative electrons. Okay. Any questions so far? Okay, now for the fun part. We're gonna play with the Van de Graaff machine again. So just a reminder, again, we didn't have a ton of time last class, so I don't know, may have rushed through the explanation. The Van de Graaff machine is yet another example of the same process. So I can rub a balloon on my shirt. I can rub silk on Teflon. I think that's what I was using. In those cases, I'm one material stealing electrons from another material. Our Van de Graaff machine up there works very similarly. It's pretty much the same idea. So I have two belts. I have one belt and I have two pulleys. I have a pulley down here connected to a motor, and I have a pulley up inside this bell. And the two pulleys are made up of two materials on either side of rubber on the triboelectric series. So if I go back to that, rubber's kind of in the middle-ish. So common Van de Graaff machine will use glass as one of the pulleys, and then maybe vinyl, PVC, Teflon, that in that category for the other pulley. And so what I can do is I just rub the rubber, as I run the rubber belt over those pulleys. One pulley is going to want to steal electrons, the other one is going to want to take them back. And so I can rapidly create this charge separation. But what is really important, and this is going to come up a couple times today, so this is an important point, and it's important to the functioning of that, is if you can see up there where it's labeled number 2 and down there where it's labeled number 7, there's these little metal combs, and you can't see them in our actual device. Nope, can't see it. There's these little metal combs, and those are actually essential to the functioning. So the way those metal combs work is they have these sharp points on them. And a big point for us today is that when you have sharp points exposed to an electric field, you're going to create you're going to basically magnify the electric field. You're going to concentrate electric field at those sharp points. And that's the same reason the Van de Graaff machine has this characteristic shape, very smooth and domey. And this is very smooth and domey. And the reason for that is I don't want to create a strong electric field, because what will happen, wherever there's a point, I'll get a very strong field at that spot. And here's, again, what's essential to the operation of this thing. Where there's a strong electric field, imagine you're an air molecule in that strong electric field. So here's a molecule that's probably not air. It could be. So imagine that's an air molecule. It's a molecule of oxygen or nitrogen or something. Put that in a strong electric field, like that picture there. A strong electric field strongly pushes and pulls on electric charges. Well, all molecules, like nitrogen, oxygen, and everything else, are made of positively charged neutrons and positively charged nuclei and electrons. One of those is going to want to go this way in the electric field, one's going to want to go this way. And so wherever I create a strong electric field, I will pull atoms like this, and if the field is strong enough, I will ionize the gas. Ionize means rip electrons off and create plasma. That's what's going on every time. Well, that's what's going on at those little combs. And that's what's also going on every time I get a spark. So if you've ever seen a spark in your life, what you were looking at was a strong electric field which ionized a gas like air, and then you got electrons flowing through that ionized gas. And the reason for that is air is not that conductive. Air is a pretty good insulator. That's why you fill your jacket with your puffy jacket with air. It's a good insulator. That's why they put air between window panes. It's a pretty good insulator. But if I ionize that air, in other words, I rip electrons off because I subject them to a strong enough electric charge, all of a sudden I've got mobile electrons. Those mobile electrons have been ripped off their parent atoms, and they can conduct really well. And so what will happen at those little combs, I'll get a very strong concentrated electric field. That field will ionize the air right at those combs, and I'll get conduction. And that is what enables this thing to work. And what happens is in this picture, and this picture is actually, again, the opposite of what we have up here. In this picture, I'm stealing electrons from the dome, and I'm depositing them onto my wand here. It's nice to have this wand. The whole point of this wand is just to be ground, to represent ground. So I'm stealing electrons from the dome, and I'm putting them on here. So I have this huge charge separation. The way this guy works, it's actually flipped. I actually I'm stealing electrons from here and depositing them on there. Same thing. So just take your two pulleys and flip them, and you'll have electrons or lack of electrons. Either way, you get a huge amount of charge. Okay. So let's see. Yeah, and then what happens is I either steal electrons from this or I deposit them. Either way, the lack of electrons or the excess of electrons ends up on the outside. And that's important. So I can continue, even with just triboelectrification, even with just rubbing, I can continue to that process. I continue that process, and I can build up a very large, well, a lot of charge, and maybe today we'll start talking about this other word called voltage. I'll actually build up a very large voltage. You may have heard like you may have heard that voltage is not, voltage doesn't kill you. I don't know, people like to say high voltage isn't that dangerous. High voltage is dangerous, it could kill you. But it's not the voltage that kills you, it's the current. I don't know if people say that. But this thing, so the wall will kill you. The wall's 120 volts. So if you plugged yourself into the wall, you could potentially die, so don't do that. That's 120 volts. This thing creates, I bet, order 500,000 volts, maybe at least 100,000 volts. It's a lot. Because, and the reason I know that is, I need at least 30,000 volts per inch, I think is about what I need, to break down air, to ionize air to make a spark. So this thing's more than that. So the wall's 120 volts. This thing's probably in the order of 100,000 volts or more. So it's a very high voltage device. Fortunately, not enough current to zap you too bad. Okay. So I think that's a pretty good explanation of the operation of that thing. I want to look at a couple examples of to demonstrate that. Let's see. One that we didn't do last class, I think I want to start with. What we didn't do last class is I'm going to turn on the Van de Graaff machine. I might even make it lower. Is this off, off? That's off, off. We'll start there. Okay. Yeah, we'll go there. So I'm going to turn on the Van de Graaff machine, and it's going to start doing its thing. It's going to start building up charge. And like I said, I think ours is the opposite of the one up there. So it's going to build up an excess of electrons. There's going to be a ton of extra electrons on that dome. They don't like each other. They're all the same charge. Like charges repel. So those electrons would like to get away from each other. Here's how they'll do that. They'll eventually build up enough voltage. They'll eventually build up enough voltage. They will ionize the air and make a spark. That's called lightning. They'll ionize the air, and they will travel through the air, and they'll make a spark. That's called lightning. And by the way, you're also hearing thunder. That little pop you're hearing, that's thunder. Thunder is air getting hot very rapidly. And in this class, we don't get into sound, but sound is just a pressure wave in air. So the air is getting, the little spark gets hot. That hot gas expands rapidly. And that expanded gas makes it to your ear, and you go, hey, that's thunder. what you're seeing up here is lightning, and what you're hearing is thunder. It's just baby version of lightning and thunder. And so what you're hearing is charge building up to the point where there's enough voltage to ionize the air, and then it's ionizing out to the air by itself. Now, if I give it a nice route to ground, it'll choose that. And so you should be able to see the purple sparks, hopefully. Oh yeah, I'm gonna keep freaking out the camera. This won't help, but I just want to zoom in. So I don't know, it's not focused, but let's see. Is that even? Yeah, we can see that on camera. Okay. So that's what you're seeing. That's lightning. That is air. That is air being ionized, and it's seeing a route to ground, and it jumps across that gap. So that what you're seeing is plasma, that's ionized air, and electrons conducting through that plasma, finding a nice route to ground. This guy is ground. So that's what we're seeing. Okay, that's a good one. Okay. Now, another good example of that we didn't do last class, this guy is creating around it an electric field. As the picture I had at the beginning of class, you can imagine, if this is negative, you can imagine a bunch of arrows pointing this thing. It's an electric field. So if I subject something to a large difference in electric field, if I subject something to a large difference in electric field, I can actually get electrons to conduct. And let's see. So this is my fluorescent tube. This is a fluorescent tube just like a normal, like in the ceiling. Let's see. Well, first of all, I'll just try this. So if I point this thing radially, at there, I'm going to have a strong field here and a weaker field over here. So I should get electrons to conduct across this. Let's see if it works. Whoa, yep. So this is just a fluorescent tube like you would use in the ceiling. And I can help myself by, let's see. And so what I want you to see is that, so I could actually just hold this thing close enough. I could hold it close enough that the electrons literally just want to jump across here and conduct through me to the ground. And I'm getting electrons running through here, and it's operating like your normal light. But I think what a better demonstration is just to see the large change in field that happens every time the Van de Graaff discharges to this. I'm seeing a large change in field, and hopefully, maybe I'll put myself on camera. So let's see that. There we go. Yeah. So every time it discharges to that sphere, I'm getting light here. Does everyone see that? So the fluorescent tube lights up not because there's electrons jumping to it. It's really the large change in field that's making that happen. Okay. And I could probably get this one to work too. Now you can actually, I don't know if you can hear it. This one actually, you're not getting big sparks, you're getting little ones because these fluorescent tubes have little sharp points on them. And I'm getting this discharge to that point. Maybe if I did it this way. Yeah, there we go. So now I'm just lighting this thing the old-fashioned way. I'm just getting current to jump up there, then go grounded through me. Like that. That's not super comfortable. Okay. All right. Any questions so far? Okay. Kaylin. Yeah, so that's a really good question. So the way these tubes work, we've talked about this before, is you need a current running through here. So this is filled with charged particles. So you need a current running through here. And so if I subject this to a strong electric field, I'll get charged particles accumulating on one end or the other. And then as soon as that field changes, they'll rearrange where they are, and I'll get a flow of electrons or a flow of charged particles of some sort. And so basically, so if I just turn this thing on and held it here, if it never popped, and it's hard to get it to not, if it never popped, I would never see any light. But it's every time there's a pop, and either to me or to this, So every time there's a pop, that's when it lights up. And that pop is the charges in there being subjected to a changing field. So they were pulled over here, and now they're not, really. And so they restored kind of, they're being pulled, and then they don't like each other because they're all like charges. So given the opportunity, they'll rearrange. And then turn the field back on, they'll go over here, and then turn it back on. So I'm getting charges just flowing inside here. Yeah, that's pretty much how I'm doing it. Question? That's a good question. So yeah, notice the camera keeps going out. So I'm creating a, I think I'm creating like basically an EMP. I don't know, from the Matrix. So in sci-fi movies, you don't want a large electromagnetic pulse. So this, like I said, this is going up to, I don't know, maybe 100,000 volts. And I'm getting a large change in field, which will create an electromagnetic pulse in the room. Not enough, your laptops are all safe, but something is picking that up. So whatever, I'm assuming that the transmission from the camera, the transmission from the camera to its source is either a radio frequency that's getting interrupted, or it's just on a wire. That wire is picking up its wire is functioning like an antenna and maybe picking up the electromagnetic pulse. So yeah, I wasn't keeping an eye on the camera the whole time. Was it continuing to freak out? Yeah, so I think every time this creates the spark, that's lightning. And lightning, that's why I'm creating a little electromagnetic pulse. Of course, it's not going to work now. And so that's a blast of electromagnetic radiation. And that's somehow either being picked up by a wire that's functioning like an antenna, or this wire that's functioning like an antenna. So yeah. We're basically making a little lightning storm in here. I think your phone and your laptop are safe, but the camera is not. Another question? Yes. Yeah. Let's see. In a big storm, power usually goes out when there's just a surge in the lines. Let's do an iClicker. I'm gonna answer your question. And then I promise we'll play more with the Van de Graaff machine. I want to leave. Oh shoot, there's already only 11. Okay, let's talk about lightning real fast. Okay, here's our iClicker for the day. Why are you safe in your car in a lightning storm? You may have heard that. A, storms are slow moving. Most cars can outrun it. B, you're sitting on rubber tires. Or C, metal cage. Or D, makes you shorter. Yeah. Okay. Let's see. Okay. All right, take 5 more seconds. 3, 2, 1. Okay, great. So you may have noticed last class I had someone stand on this plastic, because this is an insulator, plastic, so they would be not grounded. So what you don't want is the electrons flowing from here just straight through your shoes to ground. Then you're a conductive path and you're electrocuting yourself, so to speak. That has nothing to do with why we want to be in a car in a lightning storm. The rubber tires have nothing to do with it. Your tires could blow out, you could be sitting on the rims, and you'd still be fine. That's a big misconception about the whole rubber tire thing. And so I want to talk in 5 minutes. I'll talk a little bit about lightning as fast as we can, because I want to have time. I think I'll just have time in that last couple minutes class. If you want to come up here and, well, actually, I'll get at least one volunteer. Then we'll play. So class won't end. I'll have one volunteer, and then if people want to just also come up here and do it. So just like as fast as we can in the next like 4 minutes, if we can talk a little bit about lightning. So here's what's going on, and here's why your question is a good one, is that so far we've been talking a lot about electric charges. Your house and this building are powered with electricity. We pay the power company to give us a source of electricity, and that travels over power lines. So all this stuff we've been talking about right now, up till now, is very closely related to electricity. Basically, what we've been talking about up till now is just static electricity. Electricity that's not flowing. When you plug something in your wall, you just have electricity. It's moving. It's not static. Electrodynamics. Okay, so lightning is it's actually the next example of what we've been talking about. Lightning is yet another example of tribal electrification, creating a charge separation, and really hating that charge separation and wanting to go somewhere, and jumping to ground when given the opportunity. So what we've been doing up here is so similar to a lightning storm. So in a lightning storm, you have clouds. And normally clouds are big and fluffy, and they're moving around a lot, but they're not moving around as much as in a thunderstorm. In a thunderstorm, you get a lot of up and down motion in a cloud. You get freezing particles going down, you get moisture going up. All of that motion creates rubbing. And so inside a thundercloud, you just get this going on all day long. And you get a massive, massive charge separation. A thundercloud is just this. A thundercloud is just a bunch of charges that have rubbed against each other and created a massive, massive charge separation. And at the bottom of the cloud, I just get this crazy extra set of electrons, just more electrons at the bottom of the cloud. And it's just what we've been talking about so far up here, that those electrons, they'll hang out there all day long, but eventually they'll want to go somewhere. They'll want to get out of there given the chance. And they'll eventually get so strong, they'll create a strong enough electric field, they'll ionize the air. They'll create plasma. Now, the process, I think, also has a lot of misconceptions associated with it. The process is kind of complex, actually. And so you get this very strong electric field up at the cloud. That strong electric field is enough to ionize maybe a foot or so of air. That foot or so of air creates plasma, and the electrons will flow down there. But they haven't ionized, a mile-long path. You can't do that. They're not, the field up there is not big enough. The field is big enough to ionize this much air. So it ionizes this much air, and you get a little electron flowing there. And then those electrons create strong field, and they create another foot of plasma, and they flow down there, and they get another foot. And the lightning just kind of randomly does this till eventually it gets to the ground. Once it gets to the ground, it's created like a river of plasma. Now, so far, you don't really have a lightning strike. All you have is a strong field that's ionized some plasma, ionized air and created plasma in a random path and gotten to the ground. Once it gets to the ground, you've basically just plugged in the cloud. The cloud is like sweet, big fat extension cord, and the cloud dumps all its extra charge to the ground along that conductive path of plasma. And then it lights up, and then you get a rapid expansion of gas. You get light, you get excited gas, which creates light, and you get expanding gas, which creates thunder. Here's a pretty good here's a picture of it. Here's a pretty good slow-mo of it, and you can see what's going on. So first what happens is all of those little, see all those little like leaders? They're called step leaders, if I remember right. They're these little leaders that are trying to find ground. They're just ionizing air, then going there, and ionizing air and going there. Then once one of them basically wins the race and gets to ground, that's when the cloud is like, sweet, I have a big fat extension cord to ground, and now I'm just going to dump all my excess charge to ground. And then if you look very closely, the charges go down. The charges go cloud to ground, because the excess charge up here, Earth is our big ground. But if you look closely, the guys at the bottom light up first, and it's just because they were the first ones to get to ground. So there's this misconception that lightning goes up, because if you watched it, I think it looks like it went up a little bit. It's really just the ones at the bottom lit up first. but it was a discharge from cloud to ground. It's definitely that way. Okay, so just now really fast to answer your question. So now in the 2 minutes it took to explain lightning, we now know that lightning is just a lot of electrons, and the electricity or wall is a lot of electrons. So if some of that electricity ends up in the circuit or the power lines that were supposed to get to your house, something's going to blow. Usually the transformer. So usually the transformer on the pole can't handle that much current and gets hot and explodes, and then you don't have any power. That's the quickest explanation I've ever given of the power distribution network in your neighborhood and of lighting. We'll probably have to review both of those next class. We have 3 minutes left. The next thing we definitely need to do is get one more person to have their hair stand up. No? Yes? Awesome. Okay. We're going to have one person have their hair stand up to demonstrate electrostatic repulsion, and then we'll call it a day. We're not done. So let's demonstrate electrostatic repulsion. All right. Thanks. No, you're fine. That's a good. She asked. That's a really good question. She asked if she should take off her watch. No, metal. You're fine. So go ahead and put your hands on there. Really, all you're doing is just you're covering yourself in electrons. So what I'm gonna turn this on. She's now covered in electrons. The fact that she's wearing something conductive isn't going to change anything because the electrons don't. There's no really reason for the electrons to flow around there. The electrons just want to get away from each other. And so I don't know if you guys can see it, but they're already starting to flee from each other right there. Question? Oh, shoot, I didn't get to that. It's called a Faraday cage, and there's no electric field on the inside, and we'll have to start next class with a better explanation of that. But you're inside a conducting cage. So can I give you that answer? You're inside a conducting cage, and so what the lightning, well, here's what the lightning's going to do. It's going to get to that car, and it's going to go around you to ground. And you're very safe inside that conducting cage. How's it going? Can you feel it? Let's see. I don't know if you guys can see it. Whoa. There we go. Focus. It's definitely working. Your hair's, yeah. There it comes. Maybe do that. Nice. Okay, and just like last class, so she's now very charged. I don't know if you can see it. All those electrons want to get away from each other, so they've arranged themselves radially. And now, so when she takes her hands away, go ahead and take your hands away. Her hair stays standing up, but when she puts her foot on the ground, that's when she'll discharge to ground. Go for it. Yeah, thanks. Okay. So next class, we'll talk more about Faraday cages and lightning.